All right, so when we are graphing sine, where do I start for that? Say it again. Yeah, when we start graphing sine, where am I gonna start? 0. And where do I put my dot?
1.
Do I put it here?
Pi.
On sine, 0. Because cosine is our crane kick. Cosine starts up. Sine starts on the line. And where is its period going to end? It's going to go up and it's going to go down. Where does it end all the way around? Not pi. 2 pi. Because sine goes all the way around the unit circle. Halfway between, we are back on the line, but that's a full period. Sine goes up to 1, back to 0, down to -1, back to 0, like this, right? What is different about sine and cosine? What am I going to do different with cosine? So looking at cosine here, I'm going to do cosine in purple. So cosine, instead of starting at 0, starts up at 1. So cosine's going to start up here. When we get all the way through the cycle, all the way through the period for 2 pi, where's it going to be? 1. Halfway between those is when we're down on -1. Halfway between those is when we're at 0, right? So it kind of looks like this. And then like this, just so we can see our full 2 periods here. What's up? Oh, okay, I thought you said Miss B. I'm like, nah, that happened. What we're going to be looking at today is we're going to be trying to get things that are on sine shifting over to cosine. So we're going to be able to switch between those two functions. So what we're looking at is when I have things like sine of 0 is 0, right? Cosine of 0 is 1. So cosine of 0 is 1, right? Where is our nearest sine that is the same value? So, yeah, pi over 2. If I wanted to get to another value of 1 that was a sine, we need to go to sine of pi over 2 because that gives me a 1. They have that same answer, right? I can do the same thing with zeros. I could take my sine of pi is 0. We can look at that one. So if we look at, let me get a slightly different color. So if we're looking at sine of pi equals 0, where is the nearest cosine that has the same value? Yeah, be that guy over there. That's our 3 pi over 2. Cosine of 3 pi over 2 is 0. So sine and cosine are super duper similar. They're making the same shape. In fact, they're just shifted over a little bit. If I shifted it, they're identically the same function. It's just over, right? That's what I was letting us to see before I showed you guys the formulas we're going to look at because the formulas look super duper scary. How far did we move? Did I move my purple one over to make it do that? It moved over pi over 2. Whether it was for the cosine of 0 scooching over, whether it was the sine of pi scooching over, they scooched over pi over 2. That's how far apart they are. That's what we're going to be working with today. We're going to be working with complementary angles. The formulas look a little gross, but this is what it's doing. It's saying the cosine of 0 is exactly the same as sine of pi over 2. So that's what we're looking at. The formulas look like that. That's where I wanted to see what it was saying before I showed them to you. Okay. So they word it slightly different. We talked about adding pi over 2. This is saying pi over 2 minus your angle. It's just shifting it the other direction. So these are our formulas we're going to work with to find coterminal angles. What we're working towards as we get through the next section 7.3 is being able to take angles that are not unit circle angles and find their sine and cosine and tangent and those kind of stuff. Okay? So we're working to be able to take something like 47 degrees and get its sine, or 31 degrees and get its sine. So we're working to be able to fill in the rest of the values in between. So this is the way the book writes them, which is why I have them up here, even though we kind of intuitively did them the other direction. Because what they're saying here, what this first one is, our sine of pi over 2 minus theta is the same thing as cosine minus theta. They're looking at our cosine, and they took it backwards to get to the nearest side. Except that was a sine.
Are we supposed to memorize all of those?
Yeah, kind of. I mean, at least they're the same structure all the way down. When I'm just gonna say they're not the grossest. Sorry. This chapter is gonna have a lot of formulas that we have to memorize. And we should get to our second set today. Sorry. This one has a lot of formulas. But we're going to use them for a long time, but it's got quite a bit. So we're going to work with these. We're trying to find these complementary angles. These are all our cofunctions. And at least they're all the same structure. And it's always pairing together our reciprocal functions. So like sine is pairing with cosine, no matter what. Cosine pairs with sine. They're pretty much the same. Secant pairs with cosecant. Those are their buddy. And tangent and cotangent go together. So it's pairing things that make sense to go together. All of them are pi over 2 minus theta. Gets you to the other one. So it's luckily very, very similar between them. But what we're going to do is we are going to practice finding these coterminal cofunctions that we can work with. Cofunctions, not coterminal. So let's take a look at a few of them. I'm going to put it up here. It's going to have 4 of them. So we're going to put this as a cofunction of our complementary angle. That's what that means. So we're given a tangent. We want to be able to write this as a cotangent. That's what they're asking us to do. As our cofunction, it means I want to take tangent and make it be cotangent. And then that pi over 2 minus theta, that's what gives us our complementary angle. So it's putting together the cofunction and the complementary. That's what they are. So what we're going to do for our tangent of pi over 6 is we want to turn this into our cotangent of our pi over 2 minus that pi over 6. So this is just taking our formula from the previous page. Our theta is our pi over 6. Well, we're going to simplify this thing.
So is tangent always going to pair with cotangent?
Tangent will always pair with cotangent. Cosine will always pair with sine. Secant will always pair with cosecant. Their reciprocal buddies are their coterminal buddies, or cofunction buddies. Gosh, I can't say that right. So we do need to simplify that. We're having this be our cotangent of, what is pi over 2 minus pi over 6?
Pi over 3.
Pi over 3? You could put them into our, common denominators. We'd have like 3 pi over 6 minus pi over 6. We get 2 pi over 6. It becomes pi over 3. And if you go and find our unit circle values and find our tangent of pi over 6 and find our tangent of, find our cotangent of pi over 3, they will be exactly the same. We're not necessarily finding those values. We're writing it as a co-function of our complementary angle. That's our answer for that one. At some points we might. The reason we do this is because sometimes finding the tangent or the cotangent is going to be easier. And so being able to switch them back and forth, especially when we have something like our cotangent, it's easier sometimes to do tangent. Same thing with cosine and sine, those kind of things. So sometimes it'll make things easier. At this point, we're just switching them. It's not super common that it's easier to switch them, but we're doing the thing. So here we've got cosine, and now we're going to start to see where this comes into play. Pi over 8 is not one of our unit circle values. Doesn't change what we can do with it. So I can take my cosine, and I want to write it as the co-function. So I'm going to take my cosine and turn it into which piece? Sine. That's not a pen. So cosine goes with sine of the complementary angle. So I'm going to take my pi over 2, and we're going to subtract the theta, the angle they give us, our pi over 8. So we are going to simplify inside our parentheses here. What is pi over 2 minus pi over 8? 3 pi over 8. So cosine of pi over 8 is the exact same thing as sine of 3 pi over 8. So that's the whole thing. There it is, expressed as our co-function of our complementary angle. And then sometimes we go a little bit crazy. We give them to you in degrees. What? Been a minute since we saw those. Are we going to be subtracting these from pi over 2? No. What are we going to need to subtract these from? From 90 degrees. So pi over 2 is radians, and the exact same value in degrees is 90 degrees. So when we have degrees, we're going to have to subtract it from 90. The formula is just written in radians because for the most part we're using radians. So when we put this as our co-function, secant partners with which one? Cosecant. But now we have degrees, so I'm going to take my 90 degrees, and we need to subtract our 15 degrees, 20 minutes. What are we going to get for our angle for our cosecant? What is 90 degrees minus 15 degrees in 20 minutes?
74.
74 degrees and how many minutes? 40 minutes. Because there's 60 minutes to a degree. Think of it like minutes on a clock. Okay. And then our last one on this page, we've got our tangent of 27 degrees, 35 minutes. Tangent turns into cotangent. So this, our co-function here is going to be our cotangent. Bless you. And again, we're going to take our 90 degrees and we're going to subtract the angle that we had, our 27 degrees, 35 minutes. I'm right on the edge. I made it though. Barely, but it's there. What do we get when we simplify that? What is 90 degrees minus 27 degrees, 35 minutes? I have heard a couple of things. I heard 60, and then I heard 2, and I heard 3 degrees, 25 minutes. 62. should be 62 degrees and 25 minutes, okay? So it looks super complicated in the equations, but it's all about finding our cofunction and finding our complementary angle. It just looks super complicated if I just started with those equations and we didn't talk about what it was having us do. Okay? The other big part of 7.3 uses a different kind of formulas to do a specific thing. So I'm going to give us a couple of pieces that we're going to work with first, and then I'll give you formulas and we'll practice with things. Okay? So what we're going to be doing is we're going to be finding those in-between angles, but we're going to do it using some pieces here. So we're going to be finding exact values. So we're going to get all the way down to answers. We're going to look at cosine of pi over 4 plus cosine of pi over 6. Those should be values we know. Cosine of pi over 4 is what? What is cosine of pi over 4? Root 2 over 2. What is the cosine of pi over 6? Ooh, I heard two different values. Yeah, it's our root 3 over 2. So they've asked us to add these two things together. So we have that common denominator of 2. I have square root of 2 plus square root of 3. Can I simplify that anymore? I could get a decimal answer typing that in the calculator, but manually, no. I cannot add together two things in the radicals. Agreed. It just doesn't work like that. We'd have to be able to square both sides and then be able to simplify and then re-unsquare. Like, it's a mess. It's a mess. Okay, then sometimes we'll do things with tangent. This time we also give it to you in degrees because we're just tossing all kinds of stuff at you, trying to remember things. So think about tangent of 60. And if it helps, you can do it as sine of 60 degrees over cosine of 60 degrees. What is sine of 60 degrees? Square root of 3 over 2. What is cosine of 60 degrees? 1/2. So what is our tangent of 60 degrees? It's just the square root of 3. Our over 2's cancel out. So we have our square root of 3. Then we're going to do that same process with our tangent of 225. Because honestly, we probably don't have our tangents memorized because I didn't make you do so because we can figure it out from our sine and cosine. So we want to do our sine of 225 and our cosine of 225 degrees. I was like, unless you know your tangent, and that's great, it is going to be 1. Because our sine of 225, that's our negative square root of 2 over 2. And our cosine is also a negative square root of 2 over 2, except I want that to be a different color. I'll do it with, there we go. Just so we can tell where our lines shift. And our negative square root of 2 over 2, which means our tangent of 225 is a positive 1. So what we're going to have as our answer for tangent of 60 plus our tangent of 225, we find these numbers and we add them together. Square root of 3 plus 1 is square root of 3 plus 1. They don't really combine together better unless we're switching it to a decimal. So that's our answer for that bit. Or you can put it as 1 plus square root of 3. That's also fine. It doesn't matter what order we add things in. So this is kind of leading us in what we're going to be doing. We're going to be taking our trig functions and manipulating them so they're going to look kind of gross, and then we're going to find real number answers and add them together. Okay? These are going to be our main set of formulas we're going to need to memorize for this chapter. These are going to be things we are going to use a bunch. They're a little bit weird. They're kind of awkward. I'm going to put them up. Deep breath. There's 6. Sorry. Luckily, the addition and subtraction are really close together. It's just signs that change, but they're different. I know, they're gross. I'm sorry. As far as formulas that we memorize, this is the biggest chunk that we get of formulas in one go in this semester. So I'm going to give us some time to write these down. These are our addition and subtraction formulas, and this is how we're going to fill in a majority of our in-between angles when it comes to finding out values. When I write these down, we want to make sure we're being careful. We're going to be looking at 2 different angles for each one. So sine of A plus B. So if I have a sum of angles, so sine puts a sine and a cosine in each set. When I'm adding inside my angle of sine, I add my 2 products. If I'm subtracting on sine, I'm subtracting my products. Cosine keeps things separated. Cosine puts its cosines together and its sines together. If we add in cosine, I'm subtracting sine. And if I'm subtracting in cosine, I'm adding sine. So cosine has our signs switched, flip-flop. And then tangents, just a mess. The tangents are a mess. And it's because it kind of winds up like half stacking the other ones. They are gross and generally awful. That's partly what the diploma is trying to do, I think, but that does make college harder. Alright, I'm gonna give you guys plenty of time to write these down because we're gonna use these bunches and bunches. These are important ones to have. These are gonna be ones that when it comes time for finals, I'm gonna remind you that you need to have these ones memorized. Like we're gonna use these ones a bunch. We'll have one next week. As far as the exact day, that's still in flux because
Quiz or mix?
quiz. Okay. You need more time to write these? Okay, totally fine. I want us to practice with them and use them because they are weird and they are awkward. And that's okay and normal. They're gonna feel less weird to use than they feel to write down. But I know it feels like we're writing magic. Sometimes. Okay. I'm going to switch it. Because what we're going to use this for is to find something like sine of 15. 15 is not an angle that we know off the top of our head. But what I want us to think through, I want to think about our angles we do know And if there's any two angles we know that will either add to make 15 or subtract to make 15. Yeah, if I write 45 degrees minus 30 degrees, that's the same thing as putting 15, right? So if I write this as sine of 45 degrees minus 30 degrees, I didn't change what we're being asked here. But I know the values of 45 degrees and I know the trig values of 30 degrees, and we can use that formula to figure out what the sine of 15 is. That's what this is doing. So since we have a minus sign in here, we're going to look at our sign subtraction. I'm going to put it up over here just so that we have it. That's when we have our sine of a minus b, and that's our sine of a, cosine of b, because we mix and match. Sine has the same signs, and then we're going to do sine of b, cosine a. So each pair has one of each angle. So we can take this sine of 45 degrees minus 30 degrees and rewrite this as sine of 45 degrees. I'm going to do the 30 in pink just so we can keep track. Times our cosine of 30 degrees. And then we're going to subtract our sine of 30 degrees times our cosine of 45 degrees. Okay. Just say, like, once we get moving in them, they're not brutal, but they look super gross. They look super gross. So then we're going to come through here and look at each piece individually. What is the sine of 45 degrees? Yep, square root of 2 over 2. What is cosine of 30 degrees? Square root of 3 over 2. What is sine of 30 degrees? 1/2. And cosine of 45 degrees? Root 2 over 2. Yep. Okay. Now we're down to just some, like, real number. I'm going to zoom that in just because that looks really small up here. There we go. Now we're order of operationsing. So we're going to do our multiplication here because that's what it means when they're smashed together. If I take my root 2 times root 3 over 2, what is that going to turn into? Not root 2 over root 3. Root 6. When it's multiplying, I can combine them together. Root 2 times root 3 is the same thing as having root 6 over 2. 2 times 3.
Wait, can that be over 4?
What's up?
Wait, can it not be over 4 multiplying again?
Yes, over 4. Excuse me. Because we multiply across. So multiply those guys, multiply those guys. Yes, over 4. Thank you. Boop. What do we get for our 1/2 times our square root of 2 over 2? Root 2 over 4. Yep. So then we have root 6 over 4 minus root 2 over 4. Can I simplify that more? Not really. I can write it as a single fraction, which we often will, but honestly, that's about as good as it gets. So this is what our value of sine of the angle 15 is. Okay. Questions on this one? we're gonna try another. So this one was in degrees. Let's try something in radians. Oh, snap. So now we're asked cosine of 7 pi over 12. Weird. So 7 pi over 12, that's not an angle we know. Not really. Are there any angles that we know that we could add or subtract to get to 7 pi over 12?
No. Wait.
Is there another way to do it if you don't?
At this point, no?
At this point, then just do that.
What's up?
Can we do it like, convert it into an angle?
Well, it is an angle, but I was like, if you want to try and put it in degrees, you could do it that way and see if that'll let you see something. What if we took our?
5 over 6. It's 5 pi over 6. No.
I was gonna say, think about our unit circle,
5 over 6.
right? We do our. We're getting there. Hang on. Pi over 4. Pi over 6. Pi over 3, and pi over 2, right? Those tend to be the guys we work with most. What if we put those all in terms of twelfths? So we would have 6 pi over 12, 4 pi over 12, 3 pi over 12, and 2 pi over 12. Now do we see anything that we would have a sum? 4 pi over 12 and 3 pi over 12, which is the same thing as our pi over 3 and our pi over 4. Okay, let me change the view so you're not having to zoom in on my brain. There we go. If we take our 4 pi over 12 plus 3 pi over 12, that gives me 7 pi over 12. That's the exact same thing as if I had our pi over 3 and pi over 4. Okay. So when in doubt, if you don't see it, put your unit circle at the very least quadrant 1 into the same denominator. That'll sometimes help us spot it. Because we want to find angles that we know. We're not going to put inside our sum things that we don't know, because that just makes things harder. So then we're going to look at our cosine of pi over 3 plus pi over 4. So we're going to use our cosine formula. And that puts our cosine of pi over 3, cosine pi over 4, because cosine keeps our cosines together. Cosine keeps its buddies. And then it uses our opposite sign here, so cosines then subtract our sines of those same angles. Sine pi over 3, sine pi over 4. Because cosine, since we were adding here, cosine subtracts over here. So it's got their signs that flip. Same thing, when cosine subtracts, it adds over here. So be careful with cosines because they get a little tricky. Then we're at the point where I can switch these into be numbers. What is cosine of pi over 3?
4/2.
Mm-hmm. What is cosine of pi over 4? Root 2 over 2. What is sine of pi over 3? Mm-hmm. And sine of pi over 4? Root 2 over 2. Okay, so the whole point of these is to break these down into angles that we know, angles that are on our unit circle. That's part of the reason we worked so hard on the unit circle at the beginning. What? Because now we're going to come through and do our multiplication here. So when I multiply my 1/2 times root 2 over 2, what are we going to get? Root 2 over 4. And how about for our root 3 over 2, root 2 over 2? Root 6 over 4. So the sine, or sorry, excuse me, the cosine of 7 pi over 2 is this little messy friend down here, root 2 minus root 6 over 4. Okay. So there's our answer. Let's do one more. I'm gonna give us one. It's not just quadrant 1. Because sometimes we'll ask bigger angles, like 195. So what we need is some set of angles that we know that will either add or subtract to get to 195. Do 25 and 30 because it's not one I have, but that'll work.
240 minus 45.
Would also work. I was like, I had 150 plus 45, but that, like, the others would work. There's lots of options through it. Okay, so you guys want to do, which one was, I heard 225 minus 30. 225 minus 30. Totally cool. Like, we can totally work that. There's a bunch of options you can have here, especially when we start looking at these bigger angles. We can pull from any angles on our unit circle. So absolutely, totally fine. You might not have the exact same pairing as someone else, and that's okay. And I definitely just wrote an A inside cosine. So what we're doing here is we're going to do our cosine of 225 degrees minus our, what is it, 30 degrees? Yeah, 30. Okay. So we're going to use our cosine subtraction. Cosine keeps its pieces together. So we're going to have our cosine of 225 degrees times our cosine of 30 degrees. Cosine uses the opposite sign we have here, so we're going to have a plus, and then we put our signs. Sine of 225 times sine of 30. I believe in the formula it has them switched. My brain likes them to match like this, but it doesn't really matter. So then we're going to look at each one individually. What is cosine of 225? Negative root 2 over 2. What is cosine of 30? Root 3 over 2. What is sine of 225? Negative root 2 over 2. And what is sine of 30? 1/2. So we multiply our two sets of fractions together. So we're going to wind up with negative root 6 over 4 plus negative root 2 over 4. Okay, so we can put those into a single fraction over 4, where we have our negative root 6 minus root 2. Okay, we will keep working with these formulas tomorrow. That is what a majority of this section is about, is using these sum and difference formulas. Okay. I'm going to put it up there. That's what the current schedule is. I reserve the right to change it as needed. That one.